So in the last section in 12.1, we talked about how to do inference with linear regression. And so what we were interested in looking at is what the slope of a true regression line was, or trying to estimate what the true slope or the slope of the true regression line would be. We took a sample and then we tried to say something about what would the slope of the line relating the two variables to the population be. So we would look at what the line looks like in our sample, and how could we use that to infer back to the slope of the population. But the condition, one of the main conditions that we had to have in order to do those inferences back in section 12.1 was linearity. All right, so in this section, we're going to talk about what happens if the bivariate data, the x and the y data, when we plot it, it doesn't form a line. And so we're going to basically straighten out the line. So transform the data so that it is linear. And then at that point, once we've straightened out the data, then we can now use our inference procedures that we learned in section 12.1. We can estimate what the population mean is, and we can, what the population slope is, or we could do a test about, a significance test about that slope. All right, so back in chapter 3, we learned how to analyze the relationship between two quantitative variables. So here we're dealing with numerical data. And we always had a linear pattern when we were back in chapter 3, right? We talked about correlation and all that stuff. All it had to do is based on a linear pattern or a best fit line. All right, when two variable data shows the curve relationship, then we got problems. We can't do any of the inference procedures. We can't calculate a correlation, can't do anything, because all of that is predicated on having linear data. All right, in this section, we're going to describe some simple transformations that we can do so that the curved data can be linearized. We can straighten out that nonlinear pattern. And then once the data has been linearized, we've achieved linearity in the data, then we can do least squares regression, then we can do inference procedures, right? We can try to estimate what the true slope would be, or the slope of the true regression line in the population would be, or we can test claims about it. All right, so as an example, first, what we're going to talk about is transforming data that comes in a pattern that we call a power pattern or a roots pattern. So it's the square root function that you might remember from Algebra 2, or x to some power, x squared, a quadratic, x cubed, a cubic. So this is what we're going to look at first. And so this is just a kind of a silly example, but when you go into a pizza parlor, you order pizza by its diameter. Say you want a 10-inch pizza, or 12-inch pizza, or 14-inch pizza. But the amount of pizza that you get, or that you get to eat, really depends on the area of the pizza. And that area, and assuming your pizza is a circle, we're going to assume a circle. The area of the circle is pi times the square of the radius. So the area of the round pizza with diameter x is given as this formula. So the area is pi times the diameter, which is how you order a pizza. You want a 12-inch pizza. That means 12 inches is not the radius, but it's the diameter. So we would take that diameter and cut it in half, and then we would square it and multiply that by pi. So pi r squared. If we wanted to, we could kind of bring the the 4, that when it gets squared, the 4, pull that out, this 4 here gets pulled out. And so we can think of the function as being pi over 4 times x squared. All right, and so this is a power model. So y, in this case, y represents the area. A is the coefficient out in front. That's pi divided by 4. Remember, pi is just 3.14. It's a constant. So pi over 4 is the coefficient in front. And then the p, the power that you're going to raise the x to, in this case, is 2. So it's a quadratic. All right, and so the power model in the form of y equals ax to the p is describing the relationship between x and y in this situation. So we know that the relationship between the diameter and the area of the pizza is a power model. All right, so if we were to graph this data, so what I did is I took some diameters. Let's assume I took some diameters, and then I got some pizzas, an 8-inch pizza, and I calculated the area of that pizza. And then I did a 10-inch pizza and calculated its area, and so on. And you can see that this data is clearly linear, not linear, it's curved, right? So I drew in a line to help us visualize this. Clearly not linear. And if we were to pretend that it was linear and apply a linear model to this, we would graph the data. We would see a pattern in the residual plot, indicating to us that a linear model is not appropriate. All right, so even though the area and the diameter do not have a linear model, there is a linear relationship between the area and the diameter squared. So one of the ways that we'll straighten out the data is we won't plot the diameter x against y. We will square the diameters and use that as our x. So if we look at so this was essentially the chart that we just had. But if I square those diameters, so now I have the diameter squared. So instead of 8, it's 64, and so on. If I plot that data, it is linear. So instead of using as my x value, my diameter as my x value, if I do my diameter squared, then now I have linear data, all right? So another example of this powers is, imagine that you have been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish that is caught. So you know that many of the fish caught during the tournament will be measured and then released. You are aware that using delicate scales to try to weigh a fish, so we want to who caught the heaviest fish, right? So trying to use delicate scales to weigh fish that are flopping around on a moving boat, probably not going to yield very accurate results. It would be much easier to just measure the length of the fish while on the boat. But we still want to sort of relate that to the weight, right? So is there a relationship between the length of a fish and the weight of the fish? And so that's what we want to look at and plot the weight, the length against the weight. So the length is going to be used to predict the weight of the fish. All right, you contact a marine research laboratory, and they provide you with reference data on the length in centimeters and the weight in grams for Atlantic Ocean rockfish for several sizes. And so we plot that data. So here's the data on the left that we got from the research laboratory. And we plot that data, and you can see it is clearly linear. However, if we take the lengths and we cube them, and plot those against the weights, now you can see it's much more linear. It's not perfect, but it's not a perfect line. You know, the pizza data was on a perfect line, but that was because it was all theoretical. Here we have some real live data, right? So it's not going to be perfectly linear. All right, so this transformation of the explanatory variable helps produce a graph that is pretty darn linear. Now, instead of cubing the lengths, another way we could have done this is we could have taken the weights and we could have taken the cube root of the weights. So whether we cube the lengths or whether we cube root the weights, it's really going to give us still a linear. Now, it's not exactly the same data, right? You can kind of see that these graphs are not the same. And the best fit line would not be the same, right? We wouldn't get the exact same slope. We wouldn't get the exact same equation of the line. But they're both fairly linear, okay? So we can either do the cube of the length against the weight, or we can do the length of the fish against the cube root of the weight. And so if we think about like, well, how did you know to cube it? How did you know to cube root it? Like, how do we know? Well, in the physics or the physicality of this problem, we have a fish, right? So a fish, as it grows, as it gets longer, it just doesn't get longer. It also gets wider. It also gets taller, right? So it increases in 3 dimensions, not exactly proportionately, but somewhat proportionately. So the length is 1 dimension. The fish is going to be growing in 3 dimensions. So it kind of makes sense, just the physics of the situation, that it makes sense that we would take those lengths and we would cube them. Not that the fish is, a perfect square, a perfect cube. That's not what we're talking about. But the relationship between weight and length. Weight is sort of a 3-dimensional thing. With volume and density. So the relationship makes sense that it would be cubed. All right, and once we straighten out the curved pattern in the original scatter plot, if you look at the last slide, you would see that we could fit now a least squares line to either one of these transformed data sets. All right, so when experience or theory suggests the relationship. So, knowing this fish, right, we knew it was kind of like the weight should sort of be 3-dimensional compared to the length. So that kind of suggested that we should cube it. So sometimes we can, use that knowledge of the situation, maybe the theory, if we know the physics behind it, then we can use that idea to help us determine what we need to raise something to, or if we can take the cube root, for example. All right, so here's another example. Mr. Rubin's trig calc class collected data on the length in centimeters of a pendulum and the time in seconds that the pendulum took to complete one back and forth swing. This is called the period. And here are the data. So the lengths are in centimeters. The period is how long it takes for the pendulum to go once across and back again. And so I've already kind of set up a scale for us here, and we could plot this data. And you can see it looks kind of linear. Once we actually put the data, put the best fit line on there, then it's starting to look maybe a little bit problematic. So if we think like we ran a least squares regression, we got an R² value that's really high, 0.97. So that seems like, oh, okay, maybe a linear model is appropriate. And the best fit line, if we did that, if we had, you put that data into your calculator, and you could run a least squares regression on it, and you would get the y-intercept, a plus b, x being the length. So you can see you get the y-intercept plus the slope times the length. All right. So that would give us the predicted period from the length. However, when we plot a residual plot, we kind of see that there's a little bit of a pattern here. There's a big gap in the data, right? We have one pendulum that's really long, and we have the other ones that are all kind of clustered down at the bottom. But that's not the pattern I'm talking about. I'm talking about on the far left, we're below the best fit line, and as we go to the right, we're sort of above it, and then we go farther to the right, we're back below it again. So this sort of seems like this is curved data. So a linear model is not appropriate. So we need to try to sort of straighten this data out a little bit. All right, and then if we know anything about pendulums, or if we remember anything about pendulums in physics class, we know that the period of a pendulum is equal to 2 pi divided by the square root of g. Now, g is not a variable. G is the gravitational force due to gravity. And in this case, we're going to use 980 centimeters per second squared. It's the acceleration due to gravity. And then the variable is length, and it's the square root of the length. So the physics here tells us that, oh, okay, so let's take the length and let's take the square root of them and see if that will straighten out the data. And that's because we know what the physics of this relationship should be. All right, so when we do that, we see that the r squared goes up. I mean, it was already pretty high, but now it's 0.994. That's good. And then we can so put this data in our list, and we could transform it. So we could say, like in list 3, make list 3 the square root of list 1. And so now we could have in list 3 the square root of the length data. And we could plot that against the period data and do a least squares regression based on those values. And so we could get something like this, okay? Notice totally different equation. Let's plot the residual plot. You can see, okay, this is better. We've got a kind of random scattering above and below. So this is looking a little bit better than the pattern we saw when we were plotting strictly length against the period. All right. And so now let's use this prediction model, the least squares regression model, to predict how long what the period would be for a pendulum that is 80 centimeters long. So pause the video and calculate that. All right, so we simply plug in 80 for length. So we take the square root of 80 and multiply it by 0.1921, and then we add it to the y-intercept 0.02971, and we get 1.75. So the predicted period is 1.75 seconds. And we have that plotted there, plotted there in the on the graph as well. All right, so how else might we have done this? Instead of plotting the square root of the lengths against the period, we could plot the lengths against the periods squared. And again, we got a pretty good r squared value from that 0.99. And so that gives us if we did a least squares regression. So we could do, like in list 4, we could make list 4 the square of list 2. All right, and so then we could use the length data, say we have that in list 1, and we could plot that against the list 4 where we have squared the periods. And then we could also do a linear regression in our calculators based on those two lists. All right, so a scatter plot shows a random scattering. This looks pretty good. So this kind of tells us that, all right, this is a good model, that it is fairly linear. And now let's use this to predict the period for an 80 centimeter long pendulum. Now notice that this equation that we just have here is totally different than the equation we had before, and that would be normal. We're doing two different sets, data sets, so we should have a completely different least squares regression equation. All right, so we're going to put 80 in. And so this time it looks like we get 3.05645. So wait a minute, before we got 1.75, what's going on? Well, this is not the period. This is, remember, we are predicting the period squared. So in order to get the period, we would simply take the square root of both sides of that. And sure enough, that takes us back to 1.75. And we see that in, in our graph. Right. All right, so when we do transformations using this power model, if we know what the physics is behind the equation, then we know, what power to use, right? Are we going to cube it, or are we going to take the square root of it? That kind of thing. However, sometimes we don't know. We just have data. We don't know if there's any kind of physics behind it that would, create this to be curved versus linear. So if we look at the power model, we're going to use logarithms here and sort of establish that there is a linear relationship between logarithms, and then we'll be able, if this is the case, if we can straighten out the data using logarithms, and then we can predict that we have a power model. All right, and then we can go back and try some things. So let's look at the power model. So we have y equals a, the coefficient a, times x to the p power. Okay. So this is a power model. Let's take the logarithm of both sides. So we did this in Algebra 2. You're allowed to take the logarithm of both sides of an equation. On the right side, we have the log of two different things. We have the log of a, which is a constant, and log times x to the b. And if you remember, we had this product rule in logarithms that allows us to say the log of a product is equal to the sum of the logs of the two factors of that product. All right, so we break that down, and then also we know that we have an exponent rule. So this exponent can be taken down in front of that logarithm. So you remember that that's the exponent rule for logarithms. So now you could see that we have log y is equal to log a plus p times log x. So log a, that's just a constant. P, that's also a constant. And we can think of log y as just another variable and log x as just another variable. So we have log y is equal to a plus b log x. So you can see that log x, if we're using a power model, the log of the explanatory variable x will have a linear model with the log of the responsive variable y. So if we take the log of both x and y, and we show that we see a linear pattern between the log x and log y, then that means a power model is appropriate. So if the power model describes the relationship between two variables, a scatter plot of the logarithms of both variables should produce a linear pattern. All right, then we can fit the least squares regression line to the transformed data and then use the linear model to make a prediction. So notice that, so you might say, okay, so it's the logarithm of x plotted against the logarithm of y gives us a linear model. How does that help us? Like, what power should I use? And so the slope of that line is p, the power. If you look back at our relationship up here, right, the slope of that resulting line suggests that that is the P, the power that we would use in that relationship. So let's investigate this transformation of curved data into a line by looking at an example. On July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet in our solar system. They had first observed this object almost 2 years earlier using a telescope in California. Okay. Originally named UB313, the potential planet is bigger than Pluto and has an average distance of about 9.5 billion miles from the sun. All right, so for reference, Earth is about 93 million miles from the sun, so considerably further. All right, could this new astronomical body, now we refer to it as Eris, be a new planet? At the time of the discovery, there were 9 known planets in our solar system. I actually think that they demoted. I forget which one, but they demoted a planet. So, but in the meantime, when this was first discovered, we had 9 planets. All right, so if we plot the data, now the data we're plotting here is distance from the sun, and the units that we're going to use are sort of an astronomical unit. And so we, just to keep things simple, we call the distance from Earth to the sun 1 astronomical unit. And then, so planets that are closer to the sun than the Earth will have less than 1 astronomical unit, and planets that are further from the sun will have more than 1 astronomical unit than Earth. Okay. And then also we're plotting the distance from the sun and the period. In other words, how long it takes that planet to circle the sun. Now, of course, I say circle. The planets do not rotate around the sun in circles. They rotate around in ellipses. So when we say the average distance from the sun, there's a maximum and minimum distance. Most of them are fairly circular. They're ellipses, but they're not super duper elongated. All right, so here's the data from the distance on the distance from the sun and the period of revolution of those planets. Now, the period is in Earth years. So of course, Earth is 1 in 1. Mars takes almost 2 years, our Earth years, for it to rotate around. Each one would have its own year, because a year is how long it takes the Earth to rotate around the sun 1 full revolution. But we're doing all the other revolutions in terms of Earth years. Okay. So there, if you look at the data, there's definitely a curve pattern to this data. Okay. All right, so let's see if we can straighten out the data or see if a power model is appropriate for this. So the question says, explain why a power model would provide a more appropriate description of the relationship between period of revolution and distance from the sun than an exponential model. Now, we haven't really talked about exponential models. That's going to be next. So why they're kind of throwing it in a little bit early before we've really talked about it, I'm not sure, but they did. Okay. So notice on the left, they've plotted the distance against the ln, the natural log of the period. And that's clearly did not straighten out the data. It's, even more curved. So remember that when we take the logs of both sides of an equation, or in this case, we log the data, the distance or the period, we can take whatever log base we want. Often we use log base 10, so we just say log instead of saying log base 10. Another common log base is E, Euler's number. And so in this case, we're not taking log base 10, we're taking the natural log base E. So again, the one on the left clearly didn't straighten out the data, but the one on the right, when we took the log of the x, plotted against the log of the y, so that would be the log of the distance plotted against the log of the period, it did seem to straighten out. And the logs that we're taking here are natural logs. All right, so the scatter plot of log of the period against just normal distance is clearly still curved. So, and that's the test that we will go check for exponential models. But so an exponential model is not appropriate because it did not straighten out that data. However, it does appear that our data is following a power model because the natural log of distance plotted against a natural log of period does seem to straighten out the data. So now you might say, well, what's the difference whether we take the natural log, ln, or whether we take log base 10? And so I created this next slide with the same data. So here you can see I plotted natural log of distance against natural log of period. This is that same plot, except I've changed the scale a little bit from what they had. And then these are log base 10 of distance and log base 10 of the period. And you can see it doesn't matter what base I take, they still straighten out the data. Now, the equation that we would write, the best fit line for both of these transformations will certainly be different. The slopes are different. If we look at like the point, like this upper point here, is somewhere, it has an x coordinate, I don't know, maybe 3.5. This upper point here has an x coordinate of about 1.6, 1.7. So you can see that they're different data, right? I mean, you can look at the data here, and it's clearly different than the data here, right? The x values are different. So the equations that we would generate when we put the log data, log of x and log of y, into a least squares regression will certainly will generate different equations, but both would be an appropriate transformation. And so for us, we're going to just test. Right now, we're just testing to see, is this a power model? And the answer would be yes, because the log of the x variable data plotted against the log of the y variable data generates a linear graph. All right, so we've got a Minitab printout here with the equation of the line. Remember that this first data value here, this 0.002544, would be the y-intercept, almost 0. We would kind of expect it to be 0, but it's 0 here. Pretty close. And then the 1.49982 is the slope of this line, okay, after we have transformed it. So you can see here that it's the natural log of the distance, and it's actually plotted against the natural log of the period as well. All right, so Minitab output from a linear regression analysis on the transformed data is shown below. Give the equation of the least squares regression line. Be sure to define any variables you use. All right, so I'm going to use, instead of using x and y's, I'm going to put natural log period hat. So it's the predicted natural log of the period. And then we just pull those values that we just talked about in. So it's a plus b x. Instead of writing x, I'm going to say the natural log of the distance from the sun. All right, so now that we have a model, they want us to use this model to predict the period of revolution for this new planet Iris, which is 9.5 billion astronomical miles. And so we just want to convert that to astronomical. So remember, the Earth is 93 million miles. And so that ratio will give us the astronomical, how many astronomical units this new planet is from the sun. So that's 102.15 astronomical units. All right, so that is our distance, and we're going to plug that into this equation. So do that and find the period. How long will it take this planet to circle around the sun in Earth years? All right, so when you plug that in, you get something like 6.939. Now, we know that that is not the correct answer, right? This planet is so far away, it's going to take a lot longer than 6.9 years for it to circle around. And so the mistake, if we stopped here, is because that value is equal to the natural log of the period. And we want the period, or the predicted period. And so if you remember back in Algebra 2, we have to sort of undo that, right? So we find the inverse function of taking the natural log of something is raising e to that same power. So the period will be equal to e raised to that number, that's 6.939, or about 1,000 years, 1,032 years it will take for this planet to circle the sun. All right, one last thing that we want to look at here is we looked at the residual plot for the linear regression in part B, and you can see here that's definitely a pattern. And so normally we would say, oh, then a linear models, then this is not linear, right? So, I mean, yes, we linearized the data and we did a pretty good job of linearizing it. And even though there's a pattern in the residual plot, look at how small those residuals are. And so those residuals are so small that we are going to say, well, yes, there's a pattern here, but it's certainly, the pattern is much smaller than it would have been if we had just gone with the original data and tried to assume it was linear. That would be absolutely no good at all. All right, so what they're asking us to do here is, do you expect the prediction in part C to be high or low or just about right, based on what you see in the pattern of this residual plot? Well, if you put in the natural log of 102.15, then that would be that's the astronomical unit. But if we look at the natural log of the x, then that would be about 4.626. And so where would that be on our scale? So if we look at the scale, it's a little bit further out. So we're talking about an x value kind of out here somewhere, not quite at 5, but somewhere here. And so in other words, the point's not in here somewhere. The point's going to be out here somewhere. And so the pattern goes high, low, and then high again. And we would probably expect that this pattern continued, that our point would be somewhere up here. So remember that the blue line going through the middle would be a zero residual. That means the predicted value would be the exact same as the actual value. But we would expect that this pattern sort of continued high, low, high, that our actual value would be higher. So that sounds like the model would predict, and that's the blue line, is going to be lower than the actual. Again, if this model if the pattern continued that we saw in this residual plot. All right. So because the residual in this case would be the actual minus the predicted, it seems likely that it would be positive. So residual would be above the line, right? It would be positive. So we would expect our prediction to be too low rather than too high. All right, so this is our homework, and it is due next class.